All right, we're going to talk about something called Newton's method for finding roots of an equation. Newton's method for finding roots of an equation. Now, you're not going to have to do this on a quiz. You're not going to have to do this on the midterm or the final or the AP test. The only time you'll have to do it is a few homework problems and then on the take-home. On the take-home, there'll be a question about this. Okay, but I think it's an interesting topic. It's a topic that I never learned in high school in calculus or even in college calculus because we didn't have the nice graphing calculator handheld technology to do it. It's something that to do by hand is just unbelievably tedious and hard to do. The idea is easy to grasp, or not bad to grasp, but the actual calculations are really tedious without something like this, like a computer, things like this. As a matter of fact, for those of you that were in the programming class, this is an idea that this is how, or a version of this, is how your calculator does that solve. Isn't that solve button great, right? That solve command. Can you just type this thing in, solve, it just solves the equation for you. How cool is that? Well, how's it doing it? Some programmer had to write, an algorithm, a series of steps for how to make that work, how to solve that. And this is where it comes from, okay? And so this is a great example of a programmer having to really know the topic that they're trying to, the problem they're trying to solve and be able to do this. So, so that's what we're going to talk about. That's why I think it's interesting to kind of know a little bit about how your calculator works and so forth. Plus, it uses calculus, so that's a bonus as far as what we want to use it for. I don't think this is something that Newton actually invented. Isaac Newton actually invented. I think it's more named after him because he uses calculus and he's kind of one of the co-inventors of the ideas that became calculus. So we're going to start with this function right here. Okay, so we're going to start with the function f of x equals x cubed plus x plus 3. It's kind of like the one we were just talking about. And we're going to want to set that equal to 0 and solve it. Now, so what we're trying to do is solve this equation. Right? We're trying to solve this equation. Now, any equation can be set equal to 0, right? I mean, no matter what equation you're trying to solve, can't you just move everything to one side? Right? You can do that with any equation you're trying to solve. You just move everything to one side and have 0 on the other side. And so any equation you can set equal to 0. So solving any equation can be turned into where does a function equal 0? Which is its roots, right? Where does it cross the x-axis? So we can turn any equation we're trying to solve into a function equals 0, which means find its roots, find where it crosses the x-axis. Now, we already said that linear, those are easy to solve. Quadratic, we have the quadratic formula, right? But you get into some of these. Trig, we can do, the unit circle, but if it's a weird trig one, we probably can't do that if it doesn't come out to nice numbers. And here's one. There's no algebraic way to solve this. So how can we solve it? How did they used to solve it before we had things like this? Well, you learned something in algebra class. You remember synthetic division? Sorta? Kinda? It's been a while ago. Okay, here's what synthetic division was. Well, first of all, we could just guess. We could just start guessing, right? For example, I could plug in a 2. Maybe 2 works, right? Let's plug in a 2. What do we get? 13. Nah, it didn't work. I was hoping to get 0, right? I was hoping to get 0. Let's plug in a 1. 5. That didn't work. But it's getting closer. It's getting better. Let's plug in a 0. 3. Ooh, we're getting something. Plug in a -1. Ooh. -2 must be it. All right, that didn't work. Should we keep going? Yeah. It's somewhere in between, isn't it? Now, actually, that's one of the theorems we're going to learn here later. But one of the things you did in Algebra 2, you actually did this in Algebra 2 when you did synthetic division. We know we had a positive value here, and then we got a negative value here. And so doesn't it have to be 0 somewhere in between them? Now, why? Couldn't the function have went down to 1 and then jumped down to -7 and just skipped right over like a big break in the graph? Couldn't it have done that? Couldn't it have? On this graph, could it? No, because what do we know about cubics? What do we know about any polynomial? They're continuous. Polynomial functions are always continuous, and continuous means no breaks or jumps or gaps, right? Stuff we've learned before. They're continuous functions. So it has to go through. When it goes on its way from 1 to -7, it's got to hit every point in between. That's actually called the intermediate value theorem, something we're going to talk about in the next few days. It's got to hit all those points in between. So it's got to be 0 somewhere in between here. So that's what you did. Now, how'd you do that? Synthetic division in algebra class allowed you to do this really quick and easy to get these numbers and plug them in. But we're not going to go through that. But that's what we would do. And so if you really wanted to know, go back to 100 years ago when I was in high school, and we didn't have much. We had calculators, but at the very beginnings of them, but we did a lot by hand. And so what you would do then, and here's where synthetic division actually came in handy, is we'd say, well, it's in between here somewhere. I'll bet it's -1.5. Now, if I had to do a lot of work, I probably wouldn't guess -1.5. I'd probably guess what? If I was doing this by hand, I wouldn't do -1.5. What would you guess? Well, yeah, as a fraction, but what I'm saying is, somebody said it a minute ago. I went from 1 down to -7. I'm trying to get it to be 0. So do I think it's halfway in between? I think it's closer to -1. So if I was having to do this by hand, I'd probably do -1.1, right? -1.1. Now, what do I got to do? I got to do -1.1 and cube it. So that's not a lot of fun. I'm going to have to multiply that out. And then, right? So but that's where synthetic division came in handy. Well, what the heck? It's worth it. It's worth a review. This is synthetic division. You don't have to write this down. But here's how we would do that. There's a 1 there. There's missing the x squared, so I put a 0. Then we put a 1, then we put a 3. Is this starting to ring a bell at all? A little bit, kind of. We would put the coefficients down. Then we would put the number we're trying to plug in. And then we would do this. We would bring down this 1. We would do 2 times 1 and write it here. 0 plus 2 is 2. 2 times 2 is 4. 1 plus 4 is 5. 2 times 5 is 10. 3 plus 10 is 13. It was a quick way to plug in a 2 into this function. Now, what was nice about it is all I had to do was multiply and add. When I go to put a 1.1 in here, I'm going to have to cube it. I don't want to take 1.1, especially if I had a bunch of decimal places, and take it times itself 3 times, right? I don't want to have to do that. Synthetic division would allow me to put in -1.1 pretty quickly here. I go 1, 0, 1, 3. I bring down my 1. I multiply those as -1.1. I add those as -1.1. I am going to have to multiply that. But I do know 11 times 11 is 121, right? This is why we had to know this stuff. That's why us old people can do 11 squared faster. We had to know that, right? It's 1.21 positive, right? Then we add those together, and we get 4. Oh, wait, that's not 13. What am I doing? That's a 1 and a 3. Jeez. Well, like I said, I'm getting old. So 1.21, I add those together, that's 3.21. Okay? Oh, God, now I got to write it. Okay, I got it. Well, okay, so I'd still have to do, but you know what? If this was like the 6th power, this would still be a lot easier, right? So multiplying that times that would be a lot easier than having to take -1.1 to the 6th power, right? Multiply that, multiply that, multiply that. So, okay, but yeah, it still was a pain. I mean, don't get me wrong, right? We were doing stuff by hand, all right? Well, anyway, I could figure out about where that's going to be. All right, but we're not going to do the synthetic division, but this is how, without technology, that was one way to figure out where it's 0. You just kept guessing, and if your teacher said you had to be accurate to 3 decimal places, oh my goodness, right? You were going to really have to just keep trying numbers, and it really got to be a mess. So, Newton's method is much faster than that, much better. Now, when you guys go through it, you're going to see it's going to take a while as we go through it, because I'm going to make you show some of the write out the steps and stuff like this for a while. And it's, God, this is long, but it's way better than what we were just talking about, right? And if I was really mean and wanted you to appreciate Newton's method, I'd make you do a bunch of these synthetic equations, then you'd appreciate it, but whatever, okay? I'll just hope you won't get too mad at me for making you do it. All right, so here's what we're gonna do. So x cubed plus x plus 3 equals 0, and we're gonna wanna solve this. Now, we're gonna use this thing called Newton's method. Now, here's how it works. Here's how it works. Let's pretend this was our cubic function. That's not. We know it's somewhere around -1, or right? We know it's somewhere around -1 is our answer. But here's one. Here's a cubic that crosses at 2, right? So if we know its graph, well, heck, that's easy, right? We can just look at it. We can see it. All right. We know the root here is 2, but let's pretend we didn't know that, right? So let's pretend it's kind of like we were doing before. We're just going to pick a number. We're going to pick a number, plug it in, see what we get. So that's what we're going to do. All right. So we're going to pick. I don't know where it is exactly, so what the heck, I'll just pick that. I'm going to pick 3.5. Why would I pick 3.5? But I got to pick something. Now, I want to plug that into the function, right? I want to plug that in, but we're going to do it as a graph. So I plug it in, and I find the y value, right? Isn't that what we were doing on that other page, right? We're plugging it in, finding the y value. Now, we hope we get 0, right? But we don't. We get this point up here. Here's what Newton said, or what Newton's method says. Newton's method says, and the key idea of Newton's method is that if you draw a tangent line, this is where the calculus comes in. If you draw a tangent line to a curve, the line is really close to being the curve, especially where the line touches, right? When the line touches a curve, they're the same at that point. And then right around that point, the line and the curve are pretty much the same. Remember that? We've talked about that. That's called locally linear, right? The curve is pretty much straight right in that small area around it. Okay, here's what we're going to do. What Newton's method says is, if you draw a tangent line at that point, if we're close to where the graph crosses the axis, then we'll be close. The line will cross about that same place. Think about that now. If we're close, sorry people watching the video, you won't see this, but I'll do it over here. If we're close, if our guess was close, then the line is going to touch the x-axis at almost the same place as the curve does. Would you agree with that? If we're close, if our guess is close, then the tangent line is going to touch the x-axis at almost the same place that the curve does. Remember, that's what we're trying to find, is where the curve touches the x-axis. So the blue line is close, we hope, to where the curve actually touches. Now, will it be easy to find where a line touches the axis? Will it be easy to find where a line is 0? Can I solve mx plus b equals 0 pretty easily? Very easily. So what Newton's method is saying is, instead of trying to solve this cubic equals 0, which we don't know how to do, let's turn it into a line equals 0, which we do know how to do. That's what it does. That's what Newton's method does. Now, what happens if my first guess is not very close, then this point's not going to be real close to where I want it. So we do it again. We figure out where the line touches the x-axis. I call this riding the tangent line. So we pick a guess, we ride the tangent line down to the x-axis, and we make that our next guess. So now we figure out where that crossed the x-axis, because that's easy to do. Set the line equal to 0. We find that point, and then we plug that back into our function and get a new point. And then what? Find the line, find the tangent line at that point. And now look where it crosses. Pretty darn close. And now let's do it again. Let's take that point. Plug it in. That's pretty darn close to 0. Let's do a tangent line there. The red line crosses almost exactly at the same point. And we could do that over and over and over again. Okay? Now, what happens if you make a bad first guess? Well, it's just going to take longer to get there. Right? What if my first guess was here? My first tangent touches there. and then the next one, and then the next one, and we would just have to keep doing it. We would just have to do it more times if you have a bad first guess. Okay? Now, I don't have another real good example, so I'll show you. I'll put another example in here later. We'll talk more tomorrow about what are some weird things that can happen if you have a bad first guess. But for right now, I just want you to understand this process. We're going to plug in a number, a first guess. We're going to do the tangent line at that point. We're going to see where the tangent line crosses the x-axis, and then we'll just repeat. That's Newton's method. All right? All it ends up involving is doing a derivative, because you need the slope, so you can get the tangent line equation, and then you set the line equation equal to 0, and you repeat, you repeat, you repeat. Now, because of time here, I'm going to let you off the hook here. I'm not going to make you do a whole bunch of crazy stuff, but let me show you what it would look like. I used a different function here, but I did some work on one here. I did a different function, but let me show you what I'm talking about. So let's say we had this function right here. Okay, let's say we had this function right here. So, and I was going to guess 1 to start with. So I would need to plug in a 1, and I got -1. I would do the derivative so I could get the slope. So I plugged a 1 into that, got the slope, so the slope is 2. So I wrote my tangent line equation right here. Okay, I went ahead and simplified it down to here. And now I solved that. I set that equal to 0, right? Because we're trying to see where does the line hit the x-axis, right? Because the line should hit the x-axis pretty close to where the curve hits. So I set 2x minus 3 equal to 0. And I found that was 1.5, so that's my next guess. So now I got to put my 1.5 into the function and see where that hits the curve. And then I'm going to do the slope. So I'm going to plug my 1.5 into the slope equation. And I got that. And then I'm going to write my equation of my line. And then I'm going to set that equal to 0. And I got 1.41666. And now I'm going to repeat. So I'm going to plug that into the function. And I got this number. Okay, maybe I should zoom in on that a little bit here. Okay. So now I plug that into the function. And I got this number. And I plug that into the slope. And I got that number. And then I wrote my equation of my line. And then I set that equal to 0. And then I got this number. Right? And I kept getting better and better estimates. Now, that's if we were going to just do the line over and over and over again. What seems like there might be a smarter way. And there is. The smarter way would be to do this. And this is the part I do want you to write down here with me now. Okay? So, I've got my function f of x. F prime of x is my derivative, my slope. Okay? So how would I write my tangent line? Well, my first guess is going to be x sub 0. So I'm going to call x sub 0 my first guess. X sub 0 is going to be my first guess. Okay? So, I plug it in, and I get f of x sub 0, right? Because that's the first thing we said we do. Right? Come back to this. First thing we do, they called it x sub 1 here. Okay, so the first thing I do, they called it x sub 1, I'm called x sub 0. So the first thing we do is take our first guess and we plug it into the function. They called it x1, f of x1, I'm calling it x sub 0. Okay, so that's that. And then my slope is f prime of x sub 0, right? So now I've got a point and I've got a slope. So let's write the equation of the tangent line. So it would be y equals right? Isn't this how we do equation of a tangent line, right? Just like this. What goes in front of the parenthesis? The slope. So what am I going to put? F prime of x sub 0. Right? That goes in front. That's the slope. And then it's x minus what? My x point, which is x sub 0. Plus my y point, which is f of x sub 0, right? In other words, instead of doing this like I did on that paper for every problem, writing each new line, and setting it equal to 0 and solving, instead of doing that over and over in every problem. Let's just do it in general and see what happens. Now, what did I want to do with that line equation then? I want to set it equal to 0. Okay, make sure you understand this now, because this is the part on this next quiz you're going to have to do. You're going to have to be able to explain kind of the process of how Newton's method is working. What we want to do is find where this line touches the x-axis. We want to find where the tangent line is 0, because that's going to be our next guess. So, we want to set this equal to 0. I ran out of room over there, but we want to set that equal to 0. And solve for what? X. This x right here. I want to solve for that. So how could I solve for that? What would I move around here? Where would I start? I want to uncover this, and I don't want to distribute. That'll be a mess. Can I subtract this over? So I'd have f prime of x sub 0 times the quantity x minus x sub 0 equals negative f of x sub 0, correct? I would have that right there. Now I'm trying to get this x by itself right here. So what can I do next? Divide by f prime. So I got x minus x sub 0 equals negative f of x sub 0 divided by f prime of x sub 0. All right? Then what? Solving for this. Add x sub 0 over. Now, instead of tacking it on at the end, I'm going to put it in front. Since this fraction is negative, I want that to be my minus. So I'm going to add this over, and I'm going to write x sub 0 minus, and then I'll have f of x sub 0 over f prime of x sub 0. Oh, that's a beautiful thing. That's a simple little formula right there. And what that's going to do is that's going to give me my x1. In other words, that's going to give me my next guess. And so to find x2, I just take x1 minus f of x1 over f prime of x1. In other words, all I have to do is take my guess, put it into the f function, put it into the f prime function, divide those, and then subtract from the initial guess. That is going to give me my next guess, and I can repeat that, and I can repeat that. Now, I'm going to show you how I want you to work this. We're going to do it kind of the longer way with a table. Now, it's still way easier than doing that synthetic division and having to find that. It's way easier than having to do the tangent lines over and over again like I just showed you. But of the ways we're going to do, it's the longest way. Then I'm going to show you a way on your calculators we can do this a little quicker. And I'll let you do some that way too. But that will be more tomorrow's homework. So for today, we're going to start with this problem we were doing, and we're going to use this formula right here, and I'll show you how I want you to do it. So we're going to start with this, and our formula we're using is this. I'm going to write it this way now. X of n plus 1 is going to be x sub n minus f of x sub n over f prime of x sub n. And that's basically Newton's method. That's how you find the next guess. That's how you find the next spot where the line touches the x-axis. And you repeat, and you repeat, and you repeat. And pretty soon, you get numbers that are starting to look the same over and over and over again. And then you know you found it. If you want 3 decimal place accuracy, you keep going till the 3rd decimal place doesn't change. And then you know you've got it. All right, here's what this is going to look like. So we're going to make ourselves a table. Okay? First entry in the table is going to be x sub n. Okay? The second entry of the table is going to be f of x sub n. The next entry in the table is going to be f prime of x sub n. Now you can get your calculators out because we're going to use our calculators here for this. The next entry in the table is going to be f of x sub n divided by f prime of x sub n. And the last entry is going to be our answer. X sub n minus f of x sub n over f prime of x sub n. In other words, I want you to write out each of the steps you go along the way. Now, on purpose here, I'm going to make our guess be not as good as it probably could be. We know it's going to be pretty close to -1. It's actually between -1 and -2, so a smart guess would be -1. We're going to start with 0. Okay, it's going to add a couple steps, but I'm going to do a couple steps with you. I'm going to leave you a couple steps to do as part of your homework. So your only homework is going to be finishing this table and then work on sample 2. Try to get sample 2, a lot of sample 2 done. Okay? All right. So here's our function. Now again, don't lose sight of what we're trying to do. We're trying to find where this function crosses the x-axis. So what we're doing is something like this, and this little formula we've come up with is we came up with that formula by setting this line equation equal to 0. Finding where this line crosses, because if we repeat and repeat and repeat, the place where the line crosses is getting closer and closer to where the curve crosses, and that's what we're trying to solve, is where does this curve cross 0. And any equation in the world can be made into something equals 0. All right, so we're going to put a 0 here. Now get your calculators handy here. Matter of fact, if I were you right now, let's type in x cubed plus x plus 3. Because that's our f. We're going to call that our f function. And then f prime would be 3x squared plus 1. So type in x cubed plus x plus 3 and hit enter. And nothing should happen. It should just be there, right? X cubed plus x plus 3. And now type in 3x squared plus 1 and hit enter. And what we're going to do is do a vertical bar kind of thing here, right? So we can quickly plug these values into f and f prime. Okay? So you can go up and grab them. All right. So get your f in there, get your f prime in there. All right. So what's f of 0? Of course, we can do that in our head pretty easily. F of 0 is 3. What's f prime of 0? That's 1. Now we want to do f divided by f prime. 3 divided by 1 is 3. Now we want to do x sub n, which is our original number here, 0, minus this column, 0 minus 3, -3. Okay. Now that gives us our next guess. So that value comes down to here. Right? -3. All right, now we want to plug that into f. So now here's where we're going to use our calculator. So go up and grab your f function, x cubed plus x plus 3. We could probably do this in our head just as fast, but that's fine. So x cubed plus x plus 3, vertical bar, x equals -3. Because at least now you can go up and grab that each time and just change what the x is. It's or whatever. Okay, what do you get? -27. Now we want to put -3 into the 3x squared plus 1. Now again, it's pretty easy to do that in your head still, because we're going to start getting decimals here pretty soon. Okay? So yeah, you can do the vertical bar with -3, or we can just type it in. What do we get? What? 28. Okay, now divide. Now we're going to take f divided by f prime. So -27 divided by 28. Let's give it as a decimal. Okay, all you have to write is 3 places, but on your calculator we want to keep more than that, because we could really get a lot of rounding error here if we're not careful. So we're going to want to use all the decimal places that you've got. We'll come back to that here in a little bit. Okay, now we want to take this number minus that. So this number, so type in -3 minus, and then go up and grab this number so you save all those decimal places. What do we get? Negative 2.036. Now that's going to be our next number here. But remember, we want to save all those decimal places. All right, so the next thing now is we want to plug this. We want f of that number now, right? So we want to plug this into this f function. So we want to do x cubed plus x plus 3 vertical bar, and then x equals this number right here. And you want to grab the one you just calculated with that's got all those decimal places. Let's finish this line together, and then I'll let you go. What do we get? Anybody? Negative 7.472. Okay, before we go too far, is somebody agreeing with that? Negative 7, it sounds reasonable. Negative 7.472. Okay. All right, now we want to take this original number, negative 2.036, and we want f prime of that number, right? So we want to plug that into 3x squared plus 1. Should be somewhere around 13, probably. 13.423, 432, okay? Main thing is you've got it in your calculator. Now we want to divide these two, right? Now we want to divide these two. What do we get? 0.4 something? 5? Oh yeah, you're right, it would be 5 something. 5, 5, 6. And now we want to take our original number, x sub n minus that fraction. So we want this minus that. And that's negative 1.479. Now we know it's somewhere around negative 1.1, negative 1.2, we think, so we're getting closer, aren't we? We can see ourselves getting closer. All right, and now we go negative 1.479, and we do it again. I think we've done about 3 steps of this. I think you've got maybe 3 steps to go. Now we should do it until we get 3 decimal place accuracy. I want you to go at least 3 more lines, okay? If you don't have 3 decimal place accuracy, you probably should go a little farther just to practice this. And 3 decimal accuracy means until the number you get over here is the same in those 3 decimal places as the one before. It didn't change. The only thing that was changing was numbers out there farther. Now, it might take more than 3 more steps, but I want you to go at least 3 because you need to practice this, because on your take-home, you're going to have to do this. And I think at least one more in the homework tomorrow. You're going to have to do one with this table, so I want you to have this process. And I'm going to show you some other some shorter ways we can get to them also. All right, so rest of the time is yours. Homework, finish this, and then work in sample 2. Get a lot of sample 2 done, because tomorrow is going to be your last day, well, kind of last day, where I specifically give you work time on sample 2. But we have a few more book problems. Not many, 3. So you don't have to get all of sample 2 done for tomorrow, but try to get, maybe half of what's left. Maybe the next multiple choice section, somewhere in that vicinity. And feel free to check with each other as you go along. You hate to have it. Once you get off one number, then it's going to throw everything off, obviously. also, and I know some of you might be interested in this, think about some of the things on the calculator you could have done to shortcut this. We did a little bit like with the vertical bar, letting you plug things in easier. I'm going to show you some stuff with the calculator you can do, that would shortcut some of this even more. So think about that and see if you got some ideas. We can talk about them tomorrow. Do what? Maybe solve. Yeah. Okay. Because I'm going to give you a shortcut, and then I'm going to give you like a super duper shortcut. But the solve would be like this super duper shortcut. Yeah. Yeah, that's the good one.